Chapter 5.7, Arithmetic and Geometric Sequences. So we're going to take a brief sort of interlude here to talk a bit about sequences. So in our last chapter we talked about pattern recognition, right? Well, sequences are all about pattern recognition. But this is going to be the chapter that has the most sort of formulas that you're going to have to know. Luckily, you will get a formula sheet with these specific formulas on them. So take a look at the formula sheet that I've posted so that you know exactly what you'll need to, what you'll be given on the exam. I will tell you, you will need to know how to use the formulas, but you will be given the specific formulas, so you don't need to memorize them. But be aware, okay, that the formulas I'm about to go over, you will need to know what the variables mean, what the when to use which formula, etc. So this chapter is a little bit different than most of the chapters that are a lot less algebraic. Like this is the most algebra that you'll have to do in this class is in this chapter. So bear with me. So what is a sequence first? A sequence is a list of numbers that are related to each other by some rule, some pattern, right? Each new number in the sequence is called a term. So for example, 1, 3, 5, 7, 9 is the sequence of odd numbers where 1 is the first term. So what is the rule for this sequence? What would be the fifth term? 1, 4, 9, 16. We want to take a moment to think about this. 1, 4, 9, and 16. How are those related? Now, yes, I could say maybe, okay, to get from 1 to 4, I add 3, but then to get from 4 to 9, I add 5, I add 7. Well, that's sort of a pattern. I'm adding different odd numbers. But can you see another way of looking at this pattern? There is something else going on here. Well, 1, 4, 9, and 16 all have something that's related about them. 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared. So the fifth term could be 5 squared, right? Now if we got it through adding, like I was showing before, 16 plus 9 is also 5 squared, 25. Right? So sometimes there's more than one way to look at how the pattern is formed, as long as it works no matter what. So either way, we could get to the conclusion that 25 should be the fifth term. Now what we're going to look at in this chapter, we're going to focus on two specific types of sequences, arithmetic and geometric. So first, arithmetic sequences. An arithmetic sequence is a sequence in which each term after the first term differs from the preceding term by a constant amount. So this, what is called common difference, which we will usually label as D, is the amount by which each pair of successive terms differs. To find the difference, we subtract any term from the term that directly follows it. Okay, so in other words, an arithmetic sequence is just one where we just keep adding the same number, or keep subtracting the same number, right? So I have a number, I add 2, I add 2, I add 2, I add 2. Or I subtract 5, I subtract 5, I subtract 5, I subtract 5. That's what an arithmetic sequence is. That's it. It's a fairly simple type of sequence to form. But what can we do with it? So if we wanted to write the first 5 terms of the arithmetic sequence, where the first term is 9 and the common difference is -4, well, we would start with first term is 9. Okay, that's easy place to start with. We start with 9. And then we just have to remember that that common difference means we're going to subtract 4, subtract 4, subtract 4, subtract 4. So what's 9 minus 4? It's 5. 5 minus 4 is 1. 1 minus 4 is -3. -3 minus 4 is -7, and so on. And we could keep going infinitely, right? But, well, what if I want to know what the 50th term was? Do I want to have to keep doing this 50 times before I get there? I mean, I could, but it would take quite a while, right? And so this is where we're going to run into our first of our formulas that, again, will be provided to you on a formula sheet, but you do need to know what each of the variables mean and how to plug into them. So, the general term in an arithmetic sequence. For an arithmetic sequence with first term A1, so A1 is what we're going to call our first term. Notice this is A with a subscript 1. We call any term A subscript its number. So if I go back real quick, this would be A1, A1. This is A2, A3, A4, A5. So we can say A5 equals 7, A4 equals -3, A3 equals 1, and so on. That's how we name the terms of a sequence. So if I asked for the 50th term, I'd be asking for A50 equals what? And again, that is a subscript 50 to say, like, that's just kind of how this terminology works. This is how we write sequences, is we use A and then a subscript number to say what term we're at. So I want to know what A50 is. That just means what is the 50th term. That's how you would read that. The 5th term is 7, so A5 is 7. The 50th term we do not know, we want to find out. Okay, so first term is A1, the common difference is D, and then we call the general term the nth term, where n is just some number, just like we saw with the inductive and deductive reasoning section. N is just some number. We call that term an. And then we can plug in for that n. We could plug in 50 to find the 50th term. We could plug in 75 to find the 75th term. We can plug in 182 to find the 182nd term. We can plug in any number for n. N is just the term number, okay? So first term A1, term number n, common difference D, and so an is the term at position n. So if it's the 50th, we'd say A50 is A1 plus 50 minus 1 times D. All right? So determine the 14th term of the arithmetic sequence whose first term is -3 and whose common difference is 7. So first we're going to write out our variables and what they are equal to. So the first term, A1, is -3, right? The first term is A1, common difference, D, and the 14th term means that n is 14. So we're looking for A14. Our goal is A14 is equal to -3 plus 14 minus 1 times 7. Okay? And then it's just a matter of put that in your calculator, simplify it, etc. And we get 88 in the end. So 88 is equal to A14, or A14 is 88. So A14 means the 14th term in the sequence. Once again, this 14 is a subscript, okay? So it's A subscript 14 equals 88. Do not divide by 14. The 14 is just part of the label, so we know we're talking about the 14th term, okay? That's just there as part of a label. It is not there as a number to mess around with. So be careful there. Okay, let's try another example. We want to write an expression for the general or nth term, an, for the sequence 1, 6, 11, 16. So here we're going to assume it's an arithmetic sequence because that's the only type of sequence we've really talked about, and it's the only one you know how to find the general term for so far. But what if you weren't given that? What if you didn't know for sure it was an arithmetic sequence? How would we find out? Well, you just test for the pattern, right? Arithmetic sequence means it has a common difference. So does this have a common difference? Well, we add 5, and would you look at that? I add 5 again, and I add 5 again, and yeah, it does have a common difference. So I can say that D is 5. And what is A1? Well, A1 is always the first term. So A1 is 1 and D is 5. So then it's just a matter of plugging into this formula. A1 is 1, D is 5. Now this is very common mistake here is N should stay as N because we're looking for the nth term. We are not looking for the 14th term. We are not looking for the 50th term. We are looking for the nth term. That means I want a variable in there. I want N to be in there. So this is the answer, 1 plus N minus 1 times 5. I simplified it by multiplying it out a little bit, so we distribute and end up with 5N minus 4, but it's still, the point is that the general nth term of the sequence has N in it. That way, if my next question was, what is A50, what is the 50th term, then I just have to plug in 50. That's all. So then I would know that the 50th term of the sequence is 5 times 50 is 250 minus 4, so 246? Yeah, 246, right? If I want to know what A14 is, I plug in 14, right? So this is the 50th term. So say A12, that's 5 times 12 minus 4, right? So that's 60 minus 4 equals 56, and that is the 12th term, and so on. So this is the nth term. It means it is the general term that I can then plug into later to find any other term that I wanted. So when you are asked to write the general term of a sequence, you should have N in it. It should just be that formula still with N in it, but D and A1 will be replaced with whatever the common difference and the first term are. That's it. The only variable left over would thus be N. All right. Now, what is one more thing we can do with these sequences? We can what's called sum them. So the sum of the first n terms of an arithmetic sequence can be found with the following formula, where a1 represents the first term and an represents the nth term. Same terminology as before, right? We call this sum Sn. Okay, so this is the sum of however many terms. So first, second, third, fourth, fifth term, right? That would be the sum of the first 5 terms. So I add them. Remember, sum means add. So if I wanted to add up the first 5 terms of a sequence, I would say, well, S5 will equal 5 times A1 plus AN over 2. So if I wanted to determine the sum of the first 25 even natural numbers, well, okay, so even natural numbers. I didn't give you the sequence, but that's one you should know, right? The even natural numbers is 2, 4, 6, 8, and so on, right? And the first 25 of those terms gets me up to 50. But if I didn't know that it got me up to 50, how would I figure it out? It's one we could figure out, right? So let's do that. So you might know that the 25th even number is 50 because it kind of makes sense, but it only kind of makes sense because you're actually doing the general term equation in your head and you just don't realize it. So let's find the general term. So AN equals, now what does AN equal? We want to look back and remember that you'll be given the formulas, but you won't be given this information, so you'll have to know how to read the formula. That AN equals A1 plus N minus 1 times D. So AN equals A1 plus N minus 1 times D. So A1 is 2. So 2 plus N minus 1 times our D is the common difference. Common difference for even numbers is going to be plus 2. So times 2. This means AN equals that. All right. And we can simplify this a little bit to get 2 plus 2n minus 2. So in other words, an equals 2n, right? Okay. But we want, our goal is S50, or sorry, is S25. Like we're looking for the 25, the sum of the first 25 terms. So what is A25? Well, that's going to be 2 times 25, which is 50. So that's how I know that 50 is going to be my highest term. Okay? So if you didn't just know that, that's fine. We can find it using our knowledge of arithmetic sequences. Now, once we have all that, we can say A1 is 2, A25 is 50, and n is 25. And that is the three things we need to plug in to find S25. S25 is 25 times 2 plus 50 over 2, which simplifies to 650. And that's something you could test, may not want to, but if you add 2 plus 4 plus 6 plus 8 plus 10, yada yada yada, down to plus 50, it should be 650. It should be something that you can verify is truly 650. Alright, so that's it for arithmetic sequences. Now let's look at the other type of common sequence that we'll run into. So far we've talked about, well, what happens when I just keep adding the same number? What's the other thing that I can do? What's another sort of the other type of operation that I could do that's related? And I don't mean subtraction because common difference involves adding negatives as well. The other sort of easy type of operation to think about is what if instead of adding the same number, I multiply by the same number? That's where we get into geometric sequences. So a geometric sequence is one in which the ratio of any term to the term that directly precedes it is a constant. That just means if we are multiplying by the same number. That's where that ratio comes from, means like if I divide one term by another, that's what a ratio is, then I get the same result every time, right? So I've multiplied, go times 3, times 3, times 3, times 3, times 5, times 5, times 5, times 5, whatever, right? This common ratio is often going to be referred to as R. Call R our common ratio, as opposed to D our common difference. Then the ratio can be found by taking any two terms and dividing the first by the previous, okay? In the same way that we can find the common difference by subtracting. So, for example, if I wanted to write the first 5 terms of the geometric sequence with first term 4 and common ratio 5, that means A1 is 4, and then I'm multiplying by 5. Common ratio means I just keep multiplying by 5, right? So 4 times 5 is 20. 20 times 5 is 100. 100 times 5 is 500. 500 times 5 is 2,500, and so on infinitely, right? But once again, I don't want to have to do infinite work here. I want to be able to say, well, what is the 50th term? And you don't have to multiply by 5 50 times to get there. Well, you do kind of, but we'll see how to simplify that. So once again, our next formula is going to be the general term of a geometric sequence. So once again, we have first term A1, common ratio R, and then nth term AN, right? So it's terminology that hopefully by this point is starting to make sense. So we get AN equals A1 times R to the power of n minus 1, where once again n is the term number, R is the common ratio, A1 is the first term, and AN is our resulting nth term. Okay, so determine the 12th term of the geometric sequence whose first term is -4 and whose common ratio is 2. So in this question, once again, you're just being given most of the facts. You just have to know what to replace. So first term -4 means that's A1. Common ratio 2 is that's R. The 12th term, well, once again, 12th term means we're looking for a 12. Like, that's what we're trying to find. But that 12 is going to be n. So we get these three facts. A1 is -4, n is 12, and r is 2. So we plug in -4 times 2 to the power of 12 minus 1, and we're going to simplify. The -4 times 2 to the 11th. This is very important. This is a very common mistake that gets made in these problems. You have to remember PEMDAS, okay? Remember PEMDAS? Exponents come before multiplication. So we take 2 to the 11th power, which is 2048, first. Do not multiply 2 times 4 together, okay? 8, or -8 to the 11th power is very different than 4 times 2048. You can test that. It's a very different number. Do not do your multiplication first. Exponents come first. So 2 to the 11th power is 2048. Then we multiply by -4 to get -8,192. So make sure you're paying attention to your order of operations. Exponents before multiplication. Okay? All right. Now, what if we wanted to write the expression for the general nth term for the sequence 2, 6, 18, 54? Once again, we don't necessarily know that this is a geometric sequence. You can assume it is based on the slide it's on, but let's say we didn't have that information. What would we do? We would first start by testing, is it arithmetic? Well, is it? +4 plus 12. Nope. It's clearly not arithmetic. So instead, we see, is it geometric? Okay, well, times 3, oh, that's promising, right? Times 3, yeah, it looks geometric. These are all the same, right? So that tells me I have a common ratio. And then I know that A1 is 2. Okay, so A1 is 2, R is 3. We do not know n because that's the point. We want the nth term. We want n to be a variable. We do not want to plug in for n because the point is to be able to plug in for it later. So we just get 2 times 3 to the n minus 1. We just leave that n right there so that I could then later ask you, well, what is the 50th term? And then you'd know A50 equals 2 times 3 to the 50 minus 1. A72 equals 2 times 3 to the 72 minus 1. See how leaving that n alone makes it easier to plug in. So we want that n there, so it's general, so it works in general for deductive cases, so that we can just have this to use as a formula for any term later. And finally, our last formula to know is, of course, just like we did for arithmetic, we're going to do the sum of the first n terms of a geometric sequence. So this is if I was going to take 2 plus 6 plus 18 plus 54 and so on. I want to sum these up. How would I find that sum without having to actually add all these numbers? So the sum of the first n terms of a geometric sequence can be found the following formula, where once again, A1 is the first term and R is the common ratio. This one's nice because we don't even need to know AN to do this. We just need R and A1. So, as long as R does not equal 1, which in most cases you're not going to be working with that, we can do this formula. To determine the sum of the first 5 terms in the geometric sequence whose first term is 4 and whose common ratio is 2. Okay, so first term 4 means A1 is 4, R is 2. First 5 terms means N is 5, and we are looking for S5. So all we need to do is plug in each of these variables. So A1, R, make sure to plug it in twice because there's 2 R's here, and N. And be very careful, this N is an exponent. make sure to work with your order of operations as well. So we get 4 times 1 minus 2 to the 5th over 1 minus 2. So first order of operations, 1 minus 2 to the 5th is 1 minus 32 over negative 1. So 1 minus 32 is negative 31. 4 times negative 31 is negative 124. And so negative 124 divided by negative 1 is positive 124, which makes a bit of sense. Once again, you always want to be thinking in this class. It's very important that you're thinking, does that answer make sense? If I start with first term 4, and I'm continuously multiplying by 2, and then I add up 5 terms, well, okay, I could actually test this one, right? So 4 times 2 gets me 8, times 2 gets me 16, times 2 gets me 32, times 2 gets me 64. What happens when I add each of these together? Well, you want to grab a calculator probably to not have to do this by hand, but I can tell you it should add up to 124 if you've done this correctly, right? It makes sense that it would. Like these 5 numbers, they're all under 100, so together 124 is a reasonable answer. So you want to think, is the answer you're getting reasonable? You didn't get a negative number, that wouldn't work, right? You didn't get, so if you had dropped this negative sign or something like that and just put negative 124, would that make sense as an answer? No, so you'd want to go back and check. Always think about, does your answer make sense? I give points for you going back and checking your work sometimes, as long as you've sort of shown that you're thinking about your answers. That partial credit matters. So make sure you're going and looking at, do your answers actually work for the problem? Do they actually make sense given the context? Is there another way you could have gotten to the answer, like actually just doing the sum? I would expect you to use the formula, but you can check your work by actually adding them up when it's a low number like this. If I asked for the sum of 50 terms, I really wouldn't expect you to do that. But it is something you could do to check your work. You want to think, of different ways to go about getting an answer.